So the base multiplier property. So I've mentioned this word base multiplier several times, but we're going to see what we mean here more explicitly in some of the tables. So these exponential functions that we're looking at were f of x equals a times b to the x, where this b is the base of the exponential part of this term. So let's say the given function describes the relation between price of a product, which we're going to call P, and the number of months the product has been on the market. And let's say this is in dollars. And this, they told us, was in months. And P of x is 100 plus 2x. And again, we're going to think about some parentheses around that variable before we substitute. So now if x is 0, so if we're going to plug in an x equal to 0, we're going to get 2 times 0, which is 0, plus 100, which is 100. And when we plug in a 1, 2 times 1 is 2, plus 100 is 102. When we substitute 2 for x, 2 times 2 is 4, plus 100 is 104, and so on. Okay, we should recognize this whole function here as being a linear function. Okay, it's in the f of x equals b plus mx, or mx plus b form. Okay, so for an input of 0, our output was 100, so our initial value here was 100, and it's increasing at a rate of 2 for every 1 increase in x. So we're increasing x by 1. Our output here keeps increasing by 2. So if we explain in context what the constant term 100 means in this function, okay, so 100 was the output when the input was 0. So that means we've got the point for an input of 0. And actually, if we put in, let's put in the units here. Input was in months, 0 months. And then the output was in dollars, $100. So this is the number of months that the product has been on the market. So this tells us that when the product first hit the market, it was selling for $100. Okay, so when this product was first sold, it's sold for $100. But now we're asked to explain in context what that constant coefficient of 2 means. Okay, so our coefficient on x here in this function. And again, that was our ratio of change in output to change in input. So this tells us that as x increases by 1, our output, which in this case is P, increases by 2. So that has no context to it. So if we put it back into the context of the problem, x was the number of months the product was on the market, and P was price in dollars. Okay, so for every additional month this product is on the market, price increases by $2. Or we could also say, using our rate of change, we could just say that the price here is changing at a constant rate of $2 per month. Now let's say the given function describes a relation between the price of some other product, product 2, and the number of months, where again we'll say that this price is in dollars, and again this is in months, inputs in months. And now it's described by this function, which we should recognize as an exponential function. Oops. So this is in the form f of x equals a times b to the x, okay, where in this case a is 5 and b is 2. Okay. And remember, this base that we have here, b, has to be greater than 0, which it is, and b cannot be 1, which it's not. Okay, so this is a legitimate base here. All right, so now if we fill in our input-output table for this particular function, so when we substitute 0 for x, again, we're going to put parentheses in that exponent before we substitute. So again, from the last lecture, we know that 2 to the 0 was 1, times 5 gives us 5. And 2 to the first is 2, times 5 is 10. 2 squared, 2 times 2 is 4, times 5 is 20. And 2 to the third, 2 times 2 times 2 is 8, times 5 is 40. So here we'll notice that as x keeps increasing by 1, over here we keep multiplying by 2. Okay, so that's our big difference between our linear and exponential functions. Linear, as we keep increasing our input by 1, our outputs, either we add or subtract a constant value. For the exponential functions, as our input keeps increasing by 1, our outputs we keep multiplying or dividing by some constant value. So now we're asked to explain in context what the 5 means in this function. So that's here in our table. Okay, that's what we got when we plugged in 0 for x. So again, this was the output when input was 0. Okay, as an ordered pair, looks like this. When we input a 0, we get an output of 5. And with the context, again, this was months and this was dollars. So this product when it first hit the market sold for $5. Yeah, or its price, we could say. When this product first hit the market, its price was, use the word from the story, its price was $5. So now explain in context what the 2 means. Okay, so the base on this exponential piece of our term here. And so again, if we go up to the table, we'll see that as we kept increasing our power here from 0 to 1 to 2 to 3, we were introducing another factor of 2. And so those outputs kept doubling. So as input increases by 1, in this case, the output kept being multiplied by 2. Okay, so in the context here, for every additional month on the market, price of this product doubled. So again, if we bought this particular item right when it hit the market, it sold for $5. Its price was $5. A month later it was 10. A month later it was 20. Okay, or we can also see, if we initially bought it, it was 5, but 2 months later, again, it would have doubled and then doubled again. So to get from 5 to 20, we can see that the price quadrupled. It was 4 times as much. Okay, so that leads us into this base multiplier property for exponential functions. So for an exponential function, okay, so not linear and not the quadratic ones that we've already looked at, but for an exponential function of the form a times b to the x, if the value of the explanatory variables increased by 1, and so in this case our explanatory variable is x, in an input-output table it is always the input. So if the inputs increase by 1, the value of the response variable, so the output, which in this case is f, and in the table it is our output column, is multiplied by b. And we saw that happen in the table above. So use the following function to answer the following. So if f of x is equal to a times 10 to the x, so again we should recognize this as an exponential function. It's in the right form. F of x equals a times b to the x, where in this case b is equal to 10. And again, that base number has to be greater than 0, and it cannot be 1, which 10 is greater than 0 and 10's not 1, so we do have a legal base here. So what happens to the output value if the input values increase from 20 to 21? Okay, so again, we don't know what that initial starting value is. Okay, so way up here, actually let's fill these in like this maybe. So when x is 0, we would plug that in, 10 to the 0 is 1, and we would get a. So we don't know exactly what that number is, but as we keep increasing by 1, we know over here, because the base is 10, we're going to keep multiplying by 10. Okay, so although we don't know what these two values are, we know to get from one to the other, since we're only adding on 1 here, we would have to multiply by 10. So what happens to the output value if the input values increase from 20 to 21? Okay, so here the input value is increased by 1. So input goes up by 1. The output value will be multiplied by 10. Now what happens to the output value if the input is increased from 30 to 32? So now here, the input goes up by 2. So in here we would have 30, 31, 32. Again, we don't know what this value is. But to go, if this goes up by 1, again the base multiplier says we would have to multiply by 10. But then it goes up by 1 again. So again, to get from this output to this one, we would again have to multiply by 10. So to get from the output value at 30, so this box, to the output value at 32, we would have to multiply by 10 and then multiply by 10 again. So our output value here would be multiplied by 10 squared, which is 100. So we could say it's multiplied by 100.